Homework Hotline, what is your emergency?
Hello everyone, welcome to the Homework Hotline.
We're here live every Tuesday and Wednesday from 4:30 to 5:30 p.m. We want to help you with your homework questions.
If you call us, we'll interact with you and walk you through your problem. Calling is really the best way to get your question answered. Our number is 720-424-1666.
Yeah, and we have a few ways you can watch us live. You can watch us on Comcast, Channel 22, Prism TV, Channel 8007, YouTube Live at Denver DPS TV, Facebook Live at EG Homework, or live stream at livestream.com, and then you search for DPS TV 22.
So we're here to help you with math and science. I'm Becca. I can help with math. Nate, who usually also helps with math, he will not be joining us today. Over here is Sam. He can help with science. I teach at Emily Griffith High School, and Sam teaches at Contemporary Learning Academy. Our two schools sponsor the show.
Yeah, and though we prefer to get your phone calls, we know that calling isn't always the easiest thing for you to do. So we have somebody monitoring social media. Jack, why don't you tell us a little bit about yourself?
Hi, I'm Jack. I'm an intern here at DPS TV. When you send in your questions, I'm the one that's going to relay that over here to get your question answered. I also will tell you the trivia question at the top of the show and give you the answer at the bottom of the show. So today's trivia question is, what is the second oldest musical instrument known to man?
Ooh.
Not the oldest, the second oldest. So
For sure.
be careful.
Is it because the oldest is just too obvious? You think that's the reason?
You know, I don't even know what the oldest is, so it's not obvious
It's
to me.
not obvious enough.
No.
Maybe not. I
We'll
don't
have to
know.
talk about that too.
We should talk about that. But, well, if you have an answer or you think you might have an answer to our trivia question, you can give us a call at the phone number I gave you earlier. It's also on the top of your screen right there. Definitely give us a call before 5:30 today, and you can win a prize. You could win 2 symphony tickets to the symphony of your choice. I keep joking that I'm going to take them. I really am if you don't call in. So take that opportunity for sure. I'd like to also give you our other contact information. As Jack mentioned, we do field questions. If you've got homework questions, we field them through our social media. So I'd like to give you all of that information right now so that you can send in your questions. The phone number is on the top of your screen. Still, that is the best way to get in contact with us, but you can send in those questions on Facebook or Twitter at the handle EG Homework. You could text in your question at 970-680-3771, or you could email Jack your questions at homework@emilygriffith.edu. So a lot of different ways that you can get those questions in. Take your choice, but get them in before 5:30 and we can answer them live. Let's go back to Jack, though, and get him to give us some of the questions that have already been sent in.
Okay, so today's first question is going to be a science question. This has to do with black versus white t-shirts, you could say. When I wear a black or dark colored t-shirt on a sunny day, it seems to feel hotter than if I wear a light colored or white shirt. What is it about the color of the shirt that makes it hotter or cooler in the sun?
Okay, yeah, so this is a question that sort of deals with how light works and what light is, and it's sort of an interesting one. So the easy answer is that your black shirt is absorbing all of the wavelengths of light, and so let's assume that you are standing outside on a sunny day. The light coming down from the sun, I think we'd mostly agree it's a whitish, maybe yellowish light, and all of that light hitting your shirt is going to be absorbed, and when all light is absorbed by an object, that object appears black. And this sort of gets to the idea that when we see something, what we're actually seeing is the light reflected off of that thing. So if you're looking at an object and it's black, there's no light being reflected back to you. If you're looking at an object and it's white, then all of the light hitting that object is being reflected back at you. And then within that, you have different colors. So for example, if we think about, so first of all, let's think about a rainbow. So a rainbow is a division of white light. It's something that happens naturally when light is prismatized through something like raindrops. So you get this white light divided into Roy-Jabiv, right? Red through violet, and all the colors that we're able to see. Then you look at something like a tree. Let's say the leaves of a tree reflect green light, and that's why leaves appear green to us. But then all the other colors, red light and blue light, for example, are absorbed by the tree. And in the case of the tree and the leaves of the tree, that's really beneficial because the light being absorbed, light is made up of small packets of energy that we refer to as photons. Those light packets, those photons, in your black shirt, they were just energizing the molecules of your black shirt and making you hot. But in the leaves of the tree, they're actually providing energy that moves electrons around, it creates the energy in the leaf for the leaf to then synthesize sugar, which is its food. It's the key to photosynthesis, is the fact that some of that light is absorbed. So anyways, in that black t-shirt, light is being absorbed, all the different wavelengths of light. It's not reflecting anything back. We see it as black. And all the light that's being absorbed is knocking the molecules of that t-shirt around and sort of speeding up their vibrations. All molecules have a natural vibration to them, which we think of as heat. But in the case of the t-shirt, the fibers, the molecules of the fibers are being knocked around, vibrating faster, and you would feel that as heat if you were outside. Just as one last thing, if we could jump to my screen, it's kind of a cool website that you can check out if you're into it. It's just an interactive optics website, or you can type in color model mixing synthesis if you wanted to check this out. But it's basically a thing that lets you take 3 colors of light. We generally divide light into red, green, and blue light. Of course, there are other colors that we see, but those are, it's an easy way to think about light. And so what you can do with this website is you can shine something like red light down, and then you can see what would happen if you mixed it with green light. And one of the things you'll notice, besides the fact that you're getting yellow, and if you're an art student, you might say, well, I definitely don't get yellow when I mix green paint and red paint. And how color mixing works is a little bit more than I'm going to get into right now. But at least one thing that we can see is the color between the red and the green is lighter than the red or the green. And indeed, if we were to bump all these up to 100, the cross-section of the 3 of them should create a white space for us. Again, because when all the wavelengths of light are together and they're reflected back to us, we see that as white. So that was a lot of extra information. Hopefully it was useful.
It is really interesting because it's not the same as paint colors, and so you would want to, I don't know, think, oh, red light and blue light, that makes purple light,
right?
You know, but not necessarily the case just because of the way that light works.
Yeah, and really we'll have to do. I've wanted to do for a while now, but an experiment. We should do a Wednesday experiment on light color mixing and just sort of see how that works. I think it'd be a cool thing to model. It's tricky in the studio because you have to get it dark and then have things that make those different colors.
Yeah.
But hopefully we'll be able to get that set up at some point, and maybe in the spring we'll be able to do that experiment.
Very cool. Yeah, no, I would be so interested in that. That'd be very cool to see.
In the meantime, though, check out that website. It's kind of
neat. Exactly. You should check that out. It is pretty cool. All right. Well, I guess let's go back to Jack and get some more questions.
Now we have a math question. This one says, in algebra, whenever it gets to where you would have to divide by 0, or 0 is the denominator in a fraction, it's just called undefined. Why is that, and what does undefined mean?
Oh, that's a really good question. Do you have an iPhone, Sam, by any chance?
Yeah.
Can we ask Siri? I always ask this question to Siri, or I have my students ask this question to Siri, because I think she has a really great answer.
What's the question I'm asking?
Let's just say, what is 5 divided by 0?
Okay, hold on. She heard everything before. So hold on. Let's ask it one more time. Siri, what is 5 divided by 0? My Siri might not be.
I'm not sure I understand.
Your Siri doesn't understand?
No, but she also has an Australian accent.
I don't know what that means. If you like, I can search the web for... She also has an Australian accent.
Put it closer to your mic so everybody can hear, and then ask Siri again.
Okay, hold on. What's the question I'm asking?
What is 5 divided by 0?
What is 5 divided by 0?
Imagine that you have 5 cookies and you split them evenly among 0 friends. How many cookies does each of your friends get? See, it doesn't make sense. So Cookie Monster gets them all. Nom nom nom.
Wow, that was a really good answer.
She has a really good explanation.
Also, you got the nice, maybe it's a British accent. I had the Australian accent, but I think I switched it to British.
Either way, it was awesome. So I really like her explanation to this. I'll just add to it a little bit, I guess. When you're thinking about dividing by 0, or when you're thinking about dividing about anything, it's you're splitting it among those things. You're saying, how many times does this go into something? So if you were to say 5 divided by 0, you're trying to make groups of 0 from 5. And you can't really do that, as Siri kind of mentioned. And so the way that we just handle that mathematically is we say that that's undefined. It's just it's something that mathematically or numerically we can't really represent with a number or a symbol or anything. Well, I guess we can represent undefined with a symbol, but other than that, it's just a concept that doesn't work out. So we actually, the symbol we use, and I'll just show you on my screen, the symbol we use for undefined is like a 0 with a slash through it. So hopefully that answered your question. I kind of took the easy way out and let Siri do it, but I really liked her explanation with the cookies of you have 5 cookies and you're trying to divide it among 0 friends. What does that even really mean? Yeah, so that's why you get an undefined when you divide by 0 or denominator of 0. All right, Jack, do we have any more questions waiting for us on social media?
We sure do. Why don't we jump to a science question here? What is the rarest blood type and why is it rare?
Oh.
Yes, what is the rarest blood type and why is it rare?
Oh, yeah.
Okay, hold on. So AB negative is the answer to that question.
AB negative.
But I was going to show you guys some stuff related to blood cell genetics. And you just caught me off guard because I was trying to make a little table. I have access to OneNote today, which normally I don't. Nate usually gets this little pad that I've got here. And I had it today. I was going to try to do something that he's done in the past to do a representation of a Punnett square, but I can't make the table that he normally makes. So I'm just gonna talk us through it.
Do you want me to draw the Punnett square?
Are you able to draw a Punnett square on your thing?
I could do it.
Yeah, that'd be awesome. I could not find that. I tried to do a table, but it didn't work the way
and it's just 4, right?
Yes, exactly.
Okay.
Exactly.
So we'll just do that, and then we'll go. It's a little bit uneven, but for the most part.
Okay, so I'll just go over some basic stuff about blood types really quickly,
Cool.
and then we'll jump to that. So I did want to talk just briefly about sort of genetics and how we think about blood type. And blood type is a really common example in a biology class that's used to sort of explain genetics. And blood type is also really interesting because it is important that you know your blood type, or that doctors know your blood type, because if you get the wrong blood type, your body can react to it, essentially attack it like as if it's some sort of a toxin or a virus or a bacteria, some sort of an invader. And you don't want that to happen. If you need to get a blood transfusion, you want that blood to sort of be welcome by your body, I guess I would say. So in general, we talk about A blood type, B blood type, and O blood type. Then there's also this thing called AB. There's a lot that we could get into here, but I'll try to keep it sort of simple. So if you have an A blood type, that means that your red blood cells have essentially little pieces on them that are called A antigens. And if you have a B blood type, you have little pieces on them that are called B antigens. And if you have an A blood type, your body is going to develop antibodies to B blood type, because you have A blood type, and so B blood type is foreign to you, and your body develops antibodies to things that might be foreign to you, which is how your body and your immune system fight disease. Alternatively, if you have a B blood type, you're going to have antibodies in your body that fight the A blood type. And so just a really simple way of thinking about it is that if you have A blood type, you're not going to be able to take B blood, and vice versa. If you have O blood type, your blood has none of those little pieces on them that code them as A or B, but your blood, your body, your immune system also has resistance to both A and B types, which can be really problematic. And then The last type of blood so the last thing about blood is that you can have what's called Rh positive blood or Rh negative blood. And that just refers to this idea that there's a protein coat, referred to as the Rh, around your red blood cells. If you're positive, you have that protein coat. If you're negative, you don't have that protein coat. But again, it's important to know what a person has in order to give them the right type of blood. So let's just think really briefly about the genetics and how this would work, how two parents might create a baby with a certain blood type. And I'll have Becca help me with that. And then I'll just sort of explain, again, I'll go back to the original question, which was what's the rarest? So, okay. So there's like a lot to consider here. But let's say that we have a parent with a dad whose blood type is AA.
Okay. So does it matter the capital or lowercase?
Oh, yeah, so we're just going to use all capitals in this one.
All capitals, okay. Because I knew blood type was a little bit different with the Punnett square.
Becca's thinking about the fact that often when we do Punnett squares, we have a gene that's just coded as like gene T, and the dominant gene is a capital T, and the recessive gene is a little t, and we're going to talk about what dominant and recessive are in just a second. But with blood, since we have these different types, we use different capital letters.
Okay.
Okay, so dad is AA. And in general in genetics, we always have two pieces of a gene, one that came from your mom and one that came from your dad. So in the case of the dad in this example, his parents gave him the A blood type, A and A. Okay, so then let's say that mom is, let's make her an AO.
Does that mean she's A or does that mean she's O?
Yeah, so let's talk about that first. So first off, the big point would be that A and B are always going to be dominant over O. So in the case where, and so let's sort of look how this mixes, and then I think that will sort of give us some information as to how this works. Okay. So Becca's going to help us out by filling in the Punnett square. And what you essentially do is you set up this 2x2 grid of 4 squares, and you fill it in based on whatever the parents are contributing to it. So in the top left square, dad is contributing an A and mom is contributing an A, creating a 25% chance of a baby with AA blood type, which is just A blood type. And then in the square to the right, we would have AA also. And then in the squares below, the two bottom squares, mom is contributing O blood type and dad is going to contribute A blood type. A is dominant over O. So even though these babies have different genotypes, meaning if you look at their genetics, the babies on the top have A and A, the babies on the bottom have A and O, they both have the same phenotype, which is to say, in the real world, it means that their blood is all A blood.
So every child has A blood.
Correct.
Okay.
So O blood tends to be fairly rare.
I got O blood. I have O blood.
And so what do you do when you have to get blood transfusions? Do they ever talk to you about it? Do you have to do that very often?
I have to receive O, but I'm a universal donor, so I can donate blood to anyone because O is recessive. Is that why?
Well, so the reason is, and this is so interesting, right? So it's Becca's blood has antibodies inside of it that essentially are going to attack either A blood or B blood if it gets put in her body. So she has got to take O type. But her blood itself, I mentioned at the beginning that A blood has these little pieces on the outside of it called antigens that code it as A type blood. B blood cells have these little pieces that code them as B type blood. But O blood has none of those little pieces. So even though your body developed the antibodies to fight the other two types, your blood has no particular code on the outside of it, so it's accepted by any of these other.
So my blood is nice. It's not harmful
to
anyone
nice.
else.
It's really nice, but your body is not
like
so nice
blood.
to other kinds of blood. Okay, I feel like we've gone a little bit beyond maybe a concise explanation here, but there are some really great websites out there where you can check out. If we jump to my screen really quick, you can just see sort of the way that different types of parents can create different types of children. This is a really simple chart here. I'll blow it up a little bit on the screen. But suffice it to say that the rarest blood type, as we talked about, as I mentioned at the beginning, was AB negative. But there are a lot of other really rare blood types. O negative is really rare. yeah, again, this gets into a really long explanation, and I want to have a little bit of time for some other questions. So.
But either way, I mean, we saw how it works.
The thing I left out
How
was
you
the
get the blood
positive
type
and
from the
negative
blood.
aspect, and that's really key to explaining why AB negative is so rare. But it's sort of getting into a really long-winded explanation.
It's biology. It's complicated.
It is, but
Our bodies are pretty intricate.
definitely. And there's lots of good websites like the one I showed you out there that can sort of help you get a sense of this. I at some point will talk in more length about how blood types work.
I like it. I think it's interesting. All right, we're going to take a little break on that note. We will. You can get some information about Emily Griffith Technical College, and then we'll see you in a minute.
Oh, I couldn't find this image on my screen.
Oh, hi. We're back.
Hey, hello.
Caught me off guard there a little bit, but good to see you guys. We're going to go back to Jack, and we're going to get a few more questions answered from our social media board.
Okay, I think it's about time for a math question, if that's okay with everybody else.
Please.
What is the value of x when 2x plus 3 equals 3x minus 4?
Tell me that equation one more time.
2x plus 3 equals 3x minus 4.
Minus 4. Okay. Cool. So we have to solve. So I'm going to guess this is a little bit more basic of an algebra equation. I say basic. It's not basic. Don't get me wrong. But based on the question, I'm going to give a little bit more information just because so we can understand the fundamentals of solving algebra equations. I put the equation on the screen that that the person asked about, and we're trying to solve for x. Anytime we're trying to solve for a variable, what our goal is that we need to isolate it. So goal is to isolate the variable. So isolate, meaning getting it by itself. So we need to keep that goal in mind. And if we keep that goal in mind, I guess really the rules are this. What we do to one side of an equation, we have to do to the other. So as long as you keep everything equal, that's kind of the golden rule of algebra, then we should be okay. And there are certain things we can do, certain strategies we can take, but as long as you do the same thing to both sides of the equation, you're all right. My rule of thumb, so if you're isolating the variable, one thing that I would like to do, or think would make a lot of sense if you're isolating it, is to get our variable all to one side of our equation. So you might notice in this equation we have variables on both sides. We have the 2x on the left and the 3x on the right. To isolate that wouldn't be easy because we have two of them. So we want to move them over to one side and then move all of our constants, and when I say constants, it's the numbers without the variables, move those to the other side so that our variable is by itself. So what I notice here, I've got 2x on this side, I have 3x on this side. It doesn't really matter which side of the equation you move them to. I tend to go to the one that there are more of them. So on the right side, I have 3x. On the left, I have 2x's. So I'm going to move them all to the right side since I already have more over there. So to move them, what I need to do is undo what they are, or do the opposite of what they are. We know that a number plus its opposite always gives us 0. So for example, if I did 2 plus negative 2, or in other words, a shorter way to do that would be 2 minus 2, we're always going to get 0. The same thing works for variables. If I did x plus negative x, so a number and its opposite, or x minus x, same thing, I'm going to get 0. And since our goal is to isolate the variable, we want to move it completely over to the other side. So I'm going to subtract 2x from the left side of the equation, and then I have to make sure I do it to the right side as well. On the left, those cancel. As I mentioned, they give us 0. And we're just left with 3 on the left side of the equation. On the right, we're doing our 3x minus 2x, because we're taking away that 2x. And we're left with just 1x, or just x, minus 4. And so we carry everything down. We want to make sure our equation stays equivalent. Every single step, it stays equivalent. Now you might notice that our variable over here, it just has this minus 4 with it. So same idea, we want to do opposite, do the inverse operation. So we're going to add 4 to both sides. And we end up getting 7 on the left and x on the right. So now that I've isolated the variable, I know what it is. I sometimes think about solving algebra equations kind of like opening a present, a gift or something. Like, imagine if you received a gift, you don't know what's on the inside because it's all wrapped up with all of these things kind of disguising it. And our only way of figuring out what it is to unwrap it and get it by itself. And then we can see what it is pretty clearly. And that's kind of the same idea with algebra equations, is we're trying to see what that variable is, and we can't really see it until we take out all the wrapping. All those other numbers around the variable is like the wrapping, for, I guess, a metaphor. I could also show us how to check it, but what we would do, I'll just kind of sum it up real quick, how to check it. We would replace our variable with the number we thought it was, 7, in our original equation, and we want to just make sure that it does make both sides equal. And it should in this case. All right, so let's go get more questions answered.
Back to science.
Back to science.
Science.
So this question is, I heard some boats are too heavy to float in rivers or lakes, but float just fine in seas and oceans. Why do things float better in salt water than in fresh water?
Sure. So Casey Orr heard correctly. That is true. Well, okay, I should be honest with you. I didn't really know this about boats because I don't actually know that much about like boats per se. I'm not a boating individual, having been landlocked most of my life. But it makes sense that there would be boats that could float on the ocean, but that could not float on lakes or streams because this has to do with density. So the basic idea is that the density of an object allows it to be buoyant on water or in a fluid. So even though a boat weighs quite a bit, right? We can just imagine a boat on a lake. Even though that boat weighs quite a bit, and if you were to take that boat and crumple it into a ball where there was no empty space inside of the boat, and you were to let it and drop it in a lake, it would surely sink right to the bottom. But because boats have greater surface area, because they divide that weight that they have over a greater surface area, and often contain empty pockets of air, which have very low density. Because of those things, boats are less dense than water, and hence they float on water. Freshwater versus saltwater is more dense than fresh water. So because saltwater is more dense than freshwater, it can keep boats that are more dense up in a way that freshwater could not. And a way to model this would be to think about the old egg in the cup experiment. So if we jump to my computer screen, there's a picture of 3 different cups with eggs inside of them. 2 of them are a little bit cloudy. But essentially what we have here is the cloudy cups are saltwater cups of different levels of saltwater, and the clear cup is freshwater. You can see in the case of the freshwater cup, the egg that they put in it sank all the way to the bottom. And that's because freshwater, while it is somewhat dense and can hold some things up, is not dense enough to hold this egg up. The cup all the way on the right has an amount of salt water that allows the egg to float in the middle. And the cup in the middle, obviously, it's got the egg all the way at the top, meaning that the cup in the middle must have more salt in it than the cup on the right, because the water in the middle cup is more dense, hence it's holding the egg further up. And this is kind of a cool experiment to do because you can see as you add salt, you can imagine, or you can actually watch the egg progress up, or you could get a series of cups and line them up, and at different levels of saltwater see how much more dense they are, how much more they were able to hold up the egg. So again, this basically just has to do with the fact that ocean water has salt in it and is therefore more dense.
Interesting. It's interesting how it has that much of an effect. It really does.
It kind of is amazing because really saltwater, it's like we're talking 4% salt, 3% salt by weight, which is like way more than we could drink. I think we talked about this on a show recently.
Last week, yeah.
Yeah, it is amazing. It's such a small amount. Well, it's like air pressure on some level, right? Like we experience air pressure all the time on the Earth, and you think, oh yeah, I can feel air, but it's not that powerful. But air pressure lifts, many ton planes into the sky, and it's that powerful. We just don't. And that actually has to do with a fairly similar thing to what we're talking about. Air being a fluid, kind of like water, but we'll leave that for another time.
Oh, I wanted you to keep going. So interested.
No, do more math.
Okay, I guess we could do math. Do we have a math question, Jack?
Oh yes, we sure do. This one has to do with cylinders and liquids and volume.
Oh, I normally just hand this off to Nathan.
Oh yeah, no geometry guy here.
Here we go.
Okay, so I have a question about finding volume. If there is a cylinder 8 inches tall and 3 inches in diameter, I can find the volume. But if it's filled 2/3 full with a liquid, what is the easiest way to find the volume of the liquid?
Okay, so let me make sure I'm writing all of this stuff down correctly. So it's 8 inches tall and the diameter
is 3 inches.
is 3 inches.
Yes.
And we want to know, okay, it's a can filled with 2/3 full with liquid. Got it. Okay. My screen, I got a nice pretty purple cylinder on our screen. And actually the question kind of gave us a hint as to what a cylinder is, because it's talking about a can. That's actually a really good real world example of a cylinder. It's pretty much a circle, and then it's straight up. It's the same size circle on the top of the cylinder as well. So one of the things we need to know when we're finding volume of a cylinder is first we want to find the volume of that circle, and then once we find the volume of the circle, we can just multiply it by its height, because we can think about it is that circle, but as many times as its height is. So we'll label this cylinder. We said it's 8 inches tall, and then the diameter, so that means the whole way across the circle here. I know this doesn't look like a circle, but I'm going to do this. Whoops. I'm going to draw the circle so that we can see maybe a little bit. So this is the can lid, and the diameter always goes across through the center, and we're saying that diameter is 3 inches long. You may recall though, so we said we had to find the area of the circle. You might recall that to find the area of a circle, we always do pi times the radius squared. So if we know the diameter, we can find the radius by dividing it by 2. The radius is just a line from the center of the circle to the edge. So it's just half of the circle. So our radius in this case is going to be 1.5 inches. So we'll use this to find the area of our circle. We'll say pi. I'm going to say 3.14, round it just to make our numbers a little bit nicer, but you could use pi as well. Times our radius squared, so 1.5 squared. And I'm just going to handy dandy calculator so that I can save some time here. So 3.14 times 1.5 squared. So that's going to give us, the area of this circle is going to be about I'll just do the whole thing, 7.065, and this would be inches squared. So that's the area of the circle, the top of the can. So you can almost like picture it as the lid. Now we need to find the volume of the whole thing. So we need to take this number and we're multiplying that by 8, and that would give us the volume of the whole thing. So do times 8 inches, and again, I'm going to use my calculator. So the volume of our cylinder here, of the whole cylinder, is going to be 56.52, and we're going to say inches cubed now, because now we have another dimension added into this. Now the question mentioned that, all right, I'm okay with finding volume, so we did find the volume, but how would I do this if the can were 2/3 full? Well, you can kind of picture the can were 2/3 full. The volume is just, it's going to be 2/3 of the volume of the can. And so if we're doing 2/3 of that, we could say 2/3 times that. So we'll do 2/3 times the volume of our can, which is 56.52 inches cubed. And if we do 2/3 of that, then we'll have the volume of the liquid that is in the can for 2/3. So I'm going to multiply this by 2/3. And we end up getting about, I'm going to say volume of the liquid is going to be, it's about 37.68 inches cubed. So the easy way to go about that would just be multiplying your volume by 2/3, or whatever fraction it is that the liquid fills up in the can. And so overall, I guess the formula would end up being 2/3 times, we said the area of that circle, so pi r squared, and then times the height of that cylinder. So I guess this would be a formula that you could use to find 2/3 of the can of liquid. So there you have it. I hope that was okay. Was maybe not as good as Nathan and his geometry, but
I thought you did really well.
But I do know the geometry. I just don't love it. It's not my favorite. So.
You're an algebra person.
I am. I'm an algebra person. It's
For
the way
calculus,
it is.
Is calculus?
Yeah, algebra, calculus,
That whole world.
that whole realm.
Sure.
It's the way it is.
Nate just likes shapes.
All right, so let's go back. We'll do another science question. Jack, you got something for us?
I sure do. What is the difference between evaporation and distillation?
Yeah, sure. So evaporation is really just a part of distillation, and also we might think of evaporation as being like something that just happens without anyone intending it to, whereas distillation is like humans doing something specifically. So distillation is related to the word still. So if we go to my screen, I've got sort of a simple picture of a still. Okay, so this is a still like one that might be used to make alcohol, for example. Now, nobody at Homework Hotline advises drinking liquor or anything like that, but alcohol is a useful thing. It's an important part of culture and history, and definitely the process by which it's made is really interesting. So essentially what you can do is, through the process of bacterial fermentation, you can end up with a liquid that is mostly water but has a little bit of alcohol in it. Ancient peoples, or maybe not so ancient peoples, but in olden times, people decided, okay, we'd really like to get more of that alcohol into whatever the beverages that we're trying to make are. So if beer or wine were those kinds of things that could be made just with fermentation of bacteria, then harder liquors are the types of things that could be made through distillation. And the concept would go that you would put this watery substance with a little bit of alcohol into the still, and then what would happen is you'd heat it from below. Alcohol evaporates more quickly than water does. It's more volatile, we say. And so as the liquid inside gets heated, more alcohol than water would evaporate off. Now, evaporation is just the process of a liquid, a molecule being part of a liquid, moving to being part of a gas. So that's something that happens all the time. You can imagine the surface of the ocean. There's lots of water molecules evaporating off the surface of the ocean into the air, going from being liquid water to steam water. But distillation is this process where I heat some kind of liquid to get the liquid to evaporate, and I particularly want one part of the liquid. So I have water and alcohol mixture, but since alcohol is more volatile, when I heat it, more alcohol will go up the little tube system here at the top of the still, and then it'll be captured by this little tube shape here, and then it'll run through a spiral like this, typically that's cooled down. And so the coolness of that spiral will make it so that the gas particles, the alcohol gas and the water gas that's in there, will turn back to liquid. And then you would get down at the bottom of this thing, you would have a liquid dripping out, which would have a higher percentage of alcohol in it, or whatever your more volatile part of that liquid was. And so it's really ingenious, and we don't just use this for the production of alcohol. We can use it for anything where you have a mixture of liquids, and one of those liquids is more volatile than the other. Or even salt water, for example. You could take salt water, just water and salt, and if you heat salt water, the water by itself will evaporate off. You could capture it, and then you'd be left with salt in the still. So anyways, evaporation, natural process, distillation, something humans do to get a purified liquid.
Distilled water, that's how it...
Or distilled water, yeah. I probably should have gone with that instead of alcohol, given that this is a television show. But I really, again, I think it's just an interesting aspect of history.
Yeah, no, it really is. It's an interesting process, too. All right, so we're going to give you our trivia question one more time. So, Jack, trivia question, what is it?
In case you missed it at the top of the show, today's question is a music history question. What is the second oldest musical instrument known to man? And again, that is the second oldest, not the oldest.
So give us a call. We are here for about 15 more minutes, so give us a call as soon as you can if you think you have an answer to that question. And in the meantime, we're gonna take a little break, and we'll see you back for an answer to that trivia question.
There's times when you wander and ponder all the labels you've received.
Believe me, I've got a few. Never mind from when, why, or how.
'Cause now, everything's different. I found the perfect place.
A space where the labels fade and I'm accepted and supported.
Check what the news reported. Emily Griffith helps all who wish to learn.
Turn towards your future while you finish the basics on your time.
Prime opportunity in this mature environment.
The only requirement is motivation and thirst for success.
Invest in your passions. There's no limit to how far you'll go.
And know that you'll have something in common with everyone here.
We all chose empowerment over standing still in fear.
A little bit about Emily Griffith again. It is a very cool place, by the way. I'm not that biased. Not that biased.
I hear that. I hear that it's cool.
It is
Even though
true.
I don't work there, but I do hear that.
It is really cool. It really is. All right. Well, I think we have time to get a couple more questions answered. So, Jack, what do you have for us?
Okay, we have a math question. It's a bit long, a lot to remember. A piggy bank contains 6 coins, $1, a $half, a quarter, a dime, nickel, and a penny. If you were to randomly take 3 coins out, how many different sets of coins could you get?
We have a dollar, a $half, a quarter, dime,
nickel, and a penny.
Okay, ask the question one more time.
If you were to randomly take 3 coins out, how many different sets of coins could you get?
Oh, okay. All right. So, actually, I'd like to come back to this because I want to look up a formula real quick for permutations and combinations.
Do you want to do a science really quick? Or
Can we do a science
wasn't
real
there
quick?
like a honeybee question somewhere? I've been looking forward to this one.
Honeybee question. What have we got?
Isn't it like, I think it's right at the top. I think it is the top
the
question.
top, very, very top. Aha,
Okay.
yes, okay.
Let's do that. I'm going to look this up real quick because it'll help my explanation.
Okay, a honeybee getting nectar or pollen from a flower is an example of which type of association? Mutualism, parasitism, scavenger and its food, or commensalism?
Nice. That was perfect, Jack. All right. So in biology, we talk about associations as like the relationship between two organisms, two living or multiple living organisms. But usually we talk about 2. and we can sort of describe different types of relationships that those organisms might have. So I'll just really quickly go through the definitions of each of the things that we're talking about, and then we'll see what honeybee best fits. Honeybee and flower. Okay, so mutualism is going to be a situation where both sides benefit. We also call this symbiosis sometimes, but it's the idea that in an interaction, both organisms that participate in that interaction get benefit. An example is there's this type of shark or whale, can't remember, but they have like little fish that live inside their mouths and keep their mouths sort of clean, we say, but they like, they do a lot of work for the larger organisms to help it keep its digestive system functioning. And then those fish get, those little fish get access to food and protection. So something like that might be an example of mutualism. Parasitism would be one benefits and actually hurts the other one in doing so. So viruses are parasites. Viruses need things that they infect to live. In fact, we talked about this on an earlier show. Viruses aren't really alive, or we don't think of them as being alive because they can't reproduce without getting into some other system and using that system's reproductive system. Scavenger and its food is just going to be, that's like a vulture that sort of waits around for something to be dead. Doesn't kill it itself, but then finds it and eats it. And then commensalism is a situation where one side of a relationship benefits and the other side doesn't get anything out of it, but it doesn't hurt it either. I can't think of a good example, but there's got to be tons. The answer to this question would be mutualism, because honeybees get the nectar and the flower gets pollinated, which allows the flower to have sex with other flowers, which is important. So since both organisms benefit, it's mutualism.
Cool.
Was that enough time?
That was great. Yeah, no, I'm ready.
Excellent.
I can answer it.
Okay, we can ask the question again.
Ask it one more time just so our viewers know exactly what we're asking.
Okay, so a piggy bank contains 6 coins, $1, $50, quarter, dime, nickel, and a penny. If you were to randomly take 3 coins out, how many different sets of coins could you get?
Okay, so this is what we're wondering to know is sets of coins. We're wanting to know how many combinations can we make with that, those different opportunities. So I was just pulling up a formula for combinations just to show you guys. So permutation would be the same idea, but that would be if the order mattered. So we won't use permutations. We'll use this combinations formula here to help us find the number of combinations that we can make with all of this. So in the formula, and we actually talked about this exclamation point last week or a few weeks ago, it's called a factorial, and I'll explain that in just a minute. But n is going to represent the set size, so the total number of items in my sample. So my set size in this case is 6 because there are 6 different options of things that we could pull out of that bag. The R in this equation is going to represent the subset size, meaning the number that we're selecting. In this case, we're picking only just 3 different things out of the bag, so our subset is going to be 3. So we're going to say our R is 3. And if you know these 2 things, you can actually find out how many different combinations we can make with it. So we're going to say C is going to be equal to n factorial, which is 6 factorial, and then over R factorial, which is 3 factorial, and then times n minus R factorial. So we'll say 6 minus 3 factorial. And I'm just going to kind of walk through the steps of simplifying this. What I want to explain is that 6 factorial, or this factorial, just what that means is we're going to be multiplying by the numbers, the consecutive numbers counting down all the way to 1. So 6 factorial is the same as that. So I'm actually going to I'm going to expand that on the top there to show you why this simplifies the way that it does. So we'll say on top we have that on our numerator. On the bottom we have 3 factorial, so we'll say 3 times 2 times 1, and that's going to be times, I'm going to highlight this here, over here is times, so 6 minus 3 is 3 again, so it's another 3 factorial. So again, I'm going to say times 3 times 2 times 1. Now, there's a reason I expanded this rather than actually multiplying these out, is because I can simplify now before multiplying and not have to do a lot of multiplication of large numbers. So I'm going to get rid of 3 over 3, because that just equals 1. 2 over 2, that just equals 1. 1 over 1 just equals 1. And so what we end up having when we simplify is on the top we have 6 times 5 times 4, and on the bottom 3 times 2 times 1. And we can just actually go ahead and multiply those out. So 6 times 5 times 4, we get 30 times 4, we give you 120. Over 3 times 2 times 1 over 6. And then 120 divided by 6 is going to give us 20. So after all that work, we found that we have 20 different combinations that can be made from this set of items. But the combination formula, it's really nice to know because it helps in all different types of situations. As long as you know your whole set and your subset, you can find out the number of combinations. So hopefully that helps. I think
Those are tricky questions, I think. That's not intuitive stuff, and you have to really understand, okay, how does this formula work to get me what I need? And what is the question even asking of me? I think it's a tough one for students.
It is, and especially knowing the difference between combination and permutation.
Right.
Combination is just when the order doesn't matter, and it could just be 3 things. Permutation would be an example of, let's say you have 6 people running a race, and you're wondering how many combinations, what are the outcomes for first, second, and third. So when the order matters, that's a permutation, and you use the permutation formula. Order doesn't matter, combination.
Like in this one, if we wanted to pull a nickel and then a quarter and then a penny.
Right. We don't really care what order we pull them out of in this case. All right. So I think we have time for one more quick question.
Oh.
Do we have a quick one?
Yeah, I suppose. I'm not sure how quick this is going to be, but we can certainly try.
We'll try.
Science, of course. I learned you're not supposed to use water to put out a fire in the kitchen if you're cooking with grease, because the fire will jump out and spread. Why does the fire and grease react that way to water?
Because this has to do with the fact that oil is not soluble in water, right? Yeah, so oil and water don't mix. And essentially the idea here is that water is polar. Water has a positive and a negative side, and oil is nonpolar. So I'm sure most people have seen maybe when you put just oil and water, or even like oil and vinegar if you're eating bread maybe at an Italian restaurant. Maybe that's a stretch. But when you put oil in water, the oil clumps together because the oil is non-magnetic and the water is magnetic. And so the oil and the water can't really attach to each other. So the oil all globs together so that the oil is touching the water, the smallest amount of oil is touching the water, just the stuff on the outside. So the oil would prefer to get into big globs. Grease you've been cooking with in the kitchen is very hot. The molecules are moving very fast. If you were to, and I've done this before and it's not pretty, take a pan full of super hot oil and turn on the sink, put it under the sink, you have all these water molecules that are hitting all this really fast-moving grease molecules, and what you essentially get is an explosion as the grease molecules try to get away from the water molecules, try to attach with each other, but they're moving at this high speed. And that can create a reaction strong enough to start a grease fire, essentially, to ignite the carbon chains in the grease.
So don't do it.
Don't do it.
So don't do it.
Yeah.
Science says.
Science says. Do what science says.
What should you use instead?
You should wait for the grease to cool down.
Wait for the grease to cool down. Or
you can also dump out the grease into something. So like in kitchens that are moving very fast, they'll sometimes have like a grease container or some way to siphon the grease off. In big kitchens, they're working with all kinds of stuff. Okay. But at your house, if you need to use that pan for something else, if you have like what I use for bacon grease, if I'm going to cook eggs in that pan, I'll put the bacon grease. I'll put a soda can or a soup can that's open. I'll cut off the top of the soda can and then just pour the really hot grease into this empty container and wait for it to cool down there and then reuse. But essentially what you want to do is cool down the grease before you dispose of it.
Makes sense. Makes a lot of sense. That's what I do. So I guess I'm doing it right. Yes.
She's doing it right.
All right. We're gonna get the answer for our trivia question now. It is time. Jack, could you tell us the trivia question one more time? And what is our answer?
The trivia question is, what is the second oldest instrument known to man? The answer to that question is the flute.
Oh.
Fun fact, the drum was actually the first instrument to be invented by man. That would be the oldest, but the second oldest would be the flute. So the flute was used just because it was easy to make, and most people didn't know that, that was the second instrument, the second oldest instrument. So in 1995, archaeologists in Slovenia discovered a bare thigh bone with 2 holes in it. They believe that's where the flute came from. They believe it was used by Neanderthals over 43,000 years ago. And since that, of course, the flute has gone through many different stages of evolution. As you know, our flutes nowadays are made out of bone. So there's that. Also, these ancient flutes have been found in Egyptian tombs. They're depicted in art. It's a part of the woodwind family, of course, all the different families of instruments. Yeah.
Does a recorder count as a flute? I'm wondering. Like a recorder?
I think so. I think a flute is a general term.
Is just in general, it's just the hollow shape with the holes in it that makes the noise.
I think so.
Making one, though, Jack was mentioning how they are relatively primitive. You can make your own flute. It's actually pretty simple. If you have just a piece of bamboo or PVC pipe, something that is like a hollow tube, you actually, if you know some math, you can make a really pretty good flute. One of the reasons why you would need to know math is because of the measurements. If you have a 2-foot piece of pipe with a 3/4 inch diameter, then what you can do is plug one end of it and then drill a hole, and then it's just different increments that you'll be drilling them in. I'm not going to say them all because I don't know. I think the visual would be a lot more helpful, but depending on where the hole is on the flute, then you get a different note from that. So knowing where to drill the holes and how far apart to drill the holes would help you get an accurate or in tune, I guess you could say, an in tune flute.
Mm-hmm.
So.
Yeah, and I think definitely if you want to build a flute on your own, I've seen people do them out of carrots. You can make
out of carrots.
Flutes, all kinds of crazy things.
You have to hollow it out, though.
You have to hollow a carrot out.
Right.
But if you want to look into building your own flute, there's definitely, I'm sure, tons of instructions on that online. I wanted to talk really briefly about just the way a flute works, and sort of the notion of so essentially, right, in a flute, sound is a wave. It's a wave of energy traveling through a medium. In the case of sound, it's through the air, right? As I speak, my vocal cords are vibrating, and the sound of my voice is carrying across the room. And with a flute, there's sort of 2 aspects to sound, right? You can make sound loud or soft, and you can make sound high and low, right? And
like pitch, right?
Pitch, exactly.
Right.
And pitch is probably the most interesting. When we think about sound, it travels as a wave through a medium. And the taller the wave is, the louder that sound is going to be. And the tighter together that wave is, the higher the pitch is going to be.
Okay.
So high frequency waves, lots of waves in a second, high pitch sound. Low frequency waves, very few waves in a second, low pitch sounds.
And so where the hole is placed on the pipe changes the frequency of the air that's flowing through the pipe.
Right. As you blow through the flute, in any case, you're making a sound, and you're changing the frequency by plugging the holes.
Gotcha. Okay. Very cool. Really interesting. All right. So we have to say goodbye. We will be back tomorrow. Nathan should be here. So you can get all of your math and science questions answered. Just send them into social media. And again, like I said, we'll be back tomorrow from 4:30 to 5:30 p.m., just like normal. We'll catch you then.